Welcome to Chem Whiteboard. In this video, we will review how to apply the particulate model of matter to explain phase behavior. The particulate model of matter is one of the most simple but useful models in chemistry. We use this model to explain and predict the physical properties and behavior of substances. There are three main assumptions in this model. Assumption 1. Any macroscopic sample of a substance is composed of a large number of tiny particles. Assumption 2. Particles are constantly moving in random directions. Because the particles tend to move faster and faster with increasing temperature, we can say that the temperature is a measure of the average kinetic energy of the particles. Higher the temperature, the higher the average kinetic energy. Assumption 3. Particles interact with each other. Interactions between the particles are stronger when the particles are closer to each other. Potential energy depends on the strength of interactions between the particles. Stronger the attractive interactions between the particles, the lower the potential energy. Let's consider a few examples to apply what we know. Which of the following options correctly arrange the three phases of hydrogen sulfide from lowest to highest potential energy? If you selected option C, you are correct. Out of the three main phases of matter, solid, liquid, and gas, the most condensed phase, solid, has the particles closest to each other, allowing the strongest interactions between the particles. Therefore, the solid phase has the lowest potential energy. The liquid phase will be between solid and gases when it comes to potential energy. Because the particles are farthest away from each other in the gas phase, the interactions between the particles are weakest in the gas phase. Therefore, the gas phase has the highest potential energy. Next, let's consider water at two different temperatures. A represents a sample at 60 degrees Celsius, while B is at 80 degrees Celsius. Which sample, A or B, has a higher average kinetic energy? Because the temperature is a measure of the average kinetic energy, sample B, system at a higher temperature, has higher kinetic energy. Now let's consider phase transitions. Phase transition is a physical process, where a substance changes from one physical state, solid, liquid, or gas, to another. For instances, when it comes to melting or freezing, we are crossing the solid-liquid boundary, and when it comes to vaporizing and condensing, we are crossing the liquid-gas boundary. The temperatures and pressures at which the phase change occur are unique to a given substance. For instance, at 1 atmospheric pressure, the melting or the freezing temperature of water is equal to 0 degrees Celsius, and the vaporizing or the condensing temperature is equal to 100 degrees Celsius. During a phase change, energy is always exchanged, absorbed or released. During melting, vaporizing and sublimation, energy is absorbed by the system. Therefore, the change in energy will be positive. On the other hand, during freezing, condensing and deposition, energy is released. Therefore, the change in energy will be negative. In our following example, let's consider how the temperature changes when we heat a water sample from 60 degrees Celsius to 120 degrees Celsius at 1 atmosphere pressure. Assuming that we heat the sample at a constant rate, if we draw the temperature versus time graph, we can expect the temperature of the liquid water to increase with time from 60 to 100 degrees Celsius. At 100 degrees Celsius, the liquid water boils. In other words, the phase changes from liquid to gas. Note that during a phase change, the temperature remains constant. Therefore, the temperature remains constant at 100 degrees Celsius when water boils. Once all the liquid water is converted to water vapor, the temperature increases with time until 120 degrees Celsius. Now let's consider the reverse of this process. Cooling a sample of water from 120 to 60 degrees Celsius at 1 atmosphere pressure. Assuming that we cool this sample at a constant rate, if you draw the temperature versus time graph, we can expect the temperature of the liquid water to decrease with time from 120 to 100 degrees Celsius. At 100 degrees Celsius, water vapor condenses to liquid water. In other words, the phase of the water changes from gas to liquid. Again, the temperature remains constant during the phase change. Once all the water vapor is converted to liquid water, the temperature decreases with time until 60 degrees Celsius. For the same example, let's draw the energy versus temperature graphs. First, let's see how the kinetic energy changes with temperature. The temperature is a measure of the average kinetic energy. Therefore, when heating, the average kinetic energy of the water sample increases as the temperature increases. On the other hand, when cooling, the average kinetic energy of the water sample decreases as the temperature drops. Note that kinetic energy is always positive. Now let's plot the change in average kinetic energy, or the delta kinetic energy, versus temperature graphs for heating and cooling. Here, the shape is similar to the kinetic energy versus temperature graphs, but the only difference is, delta energy graphs always start at zero energy. Therefore, when heating, we start at the low temperature, where the delta kinetic energy is zero, and increases with increasing temperature. On the other hand, when cooling, the delta kinetic energy is zero at the high temperature, and decreases with decreasing temperature. Next, we will consider how the potential energy changes with temperature for heating and cooling. When heating, the potential energy increases slightly with the temperature. During the phase transition, the temperature remains constant, but the potential energy increases as the phase changes from liquid to gas, resulting a vertical region in the graph. Here the supplied energy is invested to change the distance between the particles, while the average kinetic energy is not affected. Once all the liquid water is vaporized, the potential energy of the water vapor increases slightly with temperature. On the other hand, when cooling, the potential energy decreases slightly with the temperature. During the phase transition, the temperature remains constant, but the potential energy drops. Once all the water vapor is condensed, the potential energy of the liquid water will decrease slightly with temperature. Note that, in general, potential energy is negative. Now let's plot the change in potential energy, or the delta potential energy, versus temperature graphs. Again, the shape is similar to the potential energy versus temperature graphs, but the only difference is, delta potential energy graphs always start at zero energy. Therefore, when heating, we start at the low temperature, where the delta potential energy is zero, and increases with increasing temperature. On the other hand, when cooling, the delta potential energy is zero at the high temperature, and decreases with decreasing temperature. Similarly, we can draw the change in total energy versus temperature graphs for heating and cooling. At the beginning, the change in total energy is zero. When heating, both kinetic and potential energies increase. Therefore, the total energy increases with the temperature. During the phase transition, the temperature remains constant, in other words, the change in kinetic energy is zero, while potential energy increases. Once all the liquid is vaporized, the total energy will increase with the temperature as both kinetic and potential energies increase. On the other hand, when cooling, both kinetic and potential energies decrease with temperature. Therefore, the total energy decreases with the temperature. During the phase transition, the temperature remains constant. Therefore, the change in kinetic energy is zero while the total energy drops with the decreasing potential energy. Once all the water vapor is condensed, the total energy of the liquid water will decrease with the temperature. Now let's consider the change in pressure from 0.6 atmospheric pressure to 1.2 atmospheric pressure at 100 degrees Celsius for water. Compression, or increasing pressure, of a gas will decrease its potential energy until the phase transition pressure, which is 1 atmospheric pressure for water at 100 degrees Celsius. During the phase transition, pressure remains constant until the phase change is complete. Once all the gas is converted to liquid, the potential energy will decrease with increasing pressure. On the other hand, decompression, or decreasing pressure, of a liquid, will increase its potential energy. During the phase transition, pressure remains constant until the phase change is complete. Once all the liquid is converted to gas, the potential energy will continue to increase with decreasing pressure. Note that, in general, potential energy is negative. Now let's plot the change in potential energy, or the delta potential energy, as a function of pressure. Here, the shape is similar to the potential energy versus pressure graphs, but the only difference is, delta energy graphs always start at zero energy. Therefore, when compressing, we start at the low pressure, where the delta potential energy is zero, and increasing the pressure will decrease the delta potential energy. On the other hand, when decompressing, the delta potential energy is zero at the high pressure, and decreasing pressure will increase the potential energy. Because the temperature does not change, the kinetic energy is constant during this process. Therefore, the total energy is equal to the potential energy. As a result, the shape of the total energy versus pressure graph is exactly the same as potential energy versus pressure graph. I hope this video helped you review how to apply the particulate model of matter to explain phase behavior. If you have any questions or suggestions, leave a comment in the section below. Thanks for watching, and don't forget to like and subscribe.